So my name's Charlotte Pizer. I'm a PhD student at Victoria University of Wellington, and I am studying evidence of past earthquakes, mainly based just north of Napier along the Hikurangi subduction margin. So the Hikurangi subduction margin is the interface between two plates, and that's located in New Zealand, just offshore of the east coast of the North Island. And we're interested in looking for evidence of these earthquakes because they're the biggest threat to New Zealand. So they'll cause the largest earthquakes and potentially the largest tsunamis as well. So the interface is offshore, but then it dips beneath the North Island as well. And that's why there's the great potential of large tsunamis, because that displacement will occur offshore and displace the water, causing a large tsunami to propagate towards the coast. So to start with, we have to go and seek out this evidence of earthquakes. So to do that, we go into coastal areas and take long cores. So these are usually in big pipes, and we push the pipes down into the ground and then winch them back out, chop them up into metre lengths, and that's what we have here. And then we open them up and we see what's inside, and hopefully we have these big changes in sediment type that represent earthquakes. So this is one of my cores, and so just so we're aware of what this actually represents, this is the top of the core, so this represents the surface, and as we go through the lengths here, everything gradually gets older. So these sediments have been placed on top of each other, with this one being the oldest and then getting gradually younger towards the present sediment that's at the top. Okay, so the way that we kind of distinguish where evidence of earthquakes might be is we look for changes in the sediments. So what I'm doing here is just scraping the surface of the sediment to expose all of these contacts between the different units so that we can see whether the changes are really sharp, like they are here, or whether they're more gradual. So I'll take you through this core from the bottom to the top. So starting at the base here, we have this estuary environment that we can tell from the shells. And then it goes slowly up, getting more fine sediment into this silt, but still estuary because we have lots of shells in here. Then we have the evidence of the Waimea volcanic ash. We can already get a handle on how old the sediment is because we know the age of this eruption. So this eruption was around 3,500 years ago, so everything above this is younger than 3,500 years. And then it changing to a much more terrestrial environment that we think represents a forest peat. And then down to the base of the next section, it continues with this forest peat. We see the more grey silts coming in, representing a more marine environment, and then this sudden change here to this really coarse material that has fragments of shells within it as well. So we know that the change happened here from something more terrestrial below to something more marine above. So this must have represented subsidence, so the land going down because it's closer to the ocean here than it is below. We go up here through more marine sediments, and we know this because it's sandy and it has shell in, and then to the base of the next section. Getting more terrestrial here, so maybe this section is slowly uplifting. Some more organic material here, so maybe going back towards the forest environment that we saw earlier on in the core. And further up, we see this really sharp contact here where it changes from this organic silt to sand. So this could represent another earthquake here where the land suddenly went down. So then this marine environment transitions. This could be another event here, but we're not quite sure, it's less obvious. And then we go towards the top of the core and the next section, and then the top of the core, which just represents the paddock that we caught in. So we're not really interested in this much. So something that's really important for us to work out is if we see evidence of earthquakes in these cores, we need to figure out when they occurred. So I mentioned before, we know the age of this volcanic ash, so everything must be younger than it. But what we can also do is pick out things like fragments of shells, like this one, and things from the forest peat like seeds, and then we can use radiocarbon dating to get an age on these sediments to work out when the earthquakes occurred. So in order to get a good story of the earthquakes in this region, we need lots of cores to make sure that the things that we're seeing are actually represented, firstly within this valley, and then broader scale, we look in other valleys close by and then even further away, so we can try and decide how big the earthquakes are that we can see in these cores. So we really want to get a good handle on how often and how big Hikurangi subduction earthquakes are, because that type of earthquake New Zealanders haven't experienced before within historic time. So the earthquake record that we've got from Pakuratahi is really important because it shows that the land has gone up and down quite a few times within the last 3,000 years, and we don't necessarily know the sources of those earthquakes yet. So what we need to do now is date them, find out when they occurred, and then try and compare them to earthquake records from elsewhere along the margins. So the way we can do this is to look at earthquake records from onshore along the margin, but also what we're trying to do is look at offshore cores that also contain records of earthquakes so that we can stitch them together and try and get a better picture on the timing, the location of these big earthquakes, and the size of them as well.